Right, question 8 was a question about acids and alkalis. I think this is a weak topic actually. I think we definitely need to spend time on this. This was not done particularly well. So we'll definitely, certainly in my class and probably the other classes too, spend some time really getting our heads around what's going on with acids. Now, acids, by their definition, are things that release H+. Okay, so ones you're familiar with, for example, are HCl, hydrochloric acid, releases H+, and chloride ions. Or sulfuric acid, which is a bit of a strange one, releases lots of hydrogen ions and a sulfate ion. And nitric acid does something similar, so HNO3 releases a hydrogen ion, and so on. So acids release H+. Alkalis are things that release OH-, okay, like sodium hydroxide will release OH-, or lithium hydroxide, or calcium hydroxide, whatever. But pH of acids, I think this is a tough question that you need to know about. And strength and concentration are different to each other, and they're different to each other, and the difference between them is significant and not necessarily obvious unless you've studied it. So the strength of an acid is all to do with to what extent the acid dissociates or breaks apart to release H+, and the concentration is all to do with how much there is in solution. Okay, so we'll cover that in a bit of detail. So let's be really clear though that the pH is between 1 and 7, or sometimes you can actually go below pH 1, then it's acidic, and above 7 it's alkali. But this question's about acids, so let's focus just on that. So what you've been taught is that the pH scale is what we call a logarithmic scale, and that every one pH unit, so if you go from pH 1 to pH 2 to pH 3 and so on, each step of 1 means a 10 times change in the concentration of hydrogen ions. So concentration of hydrogen ions, sometimes chemists write concentration as square brackets like that, so it depends on the concentration of hydrogen ions. Now you all know right from year 7 there's something that we say is very acidic, if you like, it's got a pH 1, something that's not very acidic might be pH 6, say. So if you've got pH 1, so low pH means high hydrogen ion concentration. Okay, I'm writing this in symbols, you probably write it in words, but low pH means high hydrogen ion concentration. Higher pH therefore must mean a lower hydrogen ion concentration, so that's what we call a negative logarithmic scale. So one step change as you go from pH 1 to pH 2, it's 10 times less concentration of hydrogen ions. So that link of pH to hydrogen ion concentration is important for the kind of first mark, if you like, and particularly this idea to get a couple of marks. Right, so let's talk about those two ideas then. So strength of an acid is all to do with how well it dissociates. Now as far as you're concerned, there are essentially 3 strong acids which you know about. So you've got HCl, as I've written up, actually I've written them up here, I'm not going to write them again. HCl fully breaks apart to give H+, and sulfuric acid fully breaks apart to give H+, and the other one, I'll just write it here, is nitric acid, fully breaks apart to give H+, the nitrate ion. So you can imagine that if you've got a 1 mole per litre solution, say, of any of these acids, you'd produce a 1 mole per litre solution of hydrogen ions, or in the case of sulfuric acid, 2 mole per litre solution of hydrogen ions. So that's quite a high concentration of hydrogen ions, and give you a low pH. Whereas if you had a weak acid, so we call that a strong acid. A weak acid, though, like ethanoic acid, which you've been taught but might have forgotten, and draw it like that. The key thing you need to know is they only partially dissociate. So it's a reaction that's in equilibrium, but it lies about 99% to the left, about 1% to the right. But when it does behave like an acid, it does produce a hydrogen ion in small quantities, as well as something called the ethanoate ion. Okay, So even if you had a strong acid and a weak acid at the same concentration, the one that would produce the most hydrogen ions per decimeter cubed of water would be the strong acid, and that's the point for the second one. So stronger the acid, the greater the dissociation or ionization, and so the lower the pH. Okay, and the other idea is simply around concentration, which is a much easier idea, one that you're familiar with. That if you've got a low concentration, there's let's just two examples. So hydrochloric acid at 1 mole per litre, or hydrochloric acid at 0.1 mole per litre. The one that's at 0.1 mole per litre will be 10 times more dilute, and therefore a 1 unit higher pH. Okay, so it's linking the idea of, so more dilute or more concentrated equals a higher pH, and more concentrated equals a lower pH. So it's quite a lot there for 4 marks. It's definitely worth something that's hopefully something you'll discuss in your lessons over the last few weeks. Well, 8.2. Most of you got this, but perhaps didn't use the right language to my satisfaction at least. Many of you know that when doing a titration, you tend to start with a rough titration, and that's that one there. And look, it's a much bigger value than all the others. We do titrations normally till they're concordant. So some of you suggested, why don't they just stop after 2? And I agree, why wouldn't they have just stopped after 2 careful runs? But anyway, they did it twice more and got 4 runs with concordant data. And so the mean, it was the mean of runs 2 to 4 would have got one of the marks there. The mean of runs 2 to 4 there would have got the mark. And then let's go with that. What else were you allowed to say? Yeah, that's fine. The mean of runs 2 to 4 for them. Oh, 2 to 5. Sorry, those 4 numbers. The this one there was ignored. You could simply say because it was a rough titration, or that it was an anomaly or anomalous data. And there's some interesting spellings of anomaly, which was good fun. But that's the other one. So run 1, rough or anomalous. I hope I've spelled that right now. Okay, I've spelled it right. That's a relief. There we are. That's that one. Question 8.3. Again, a moles question, but this time it was a volume and concentration moles question. So there's quite a variety in this paper, and I like that, and I hope that was a good challenge for you. I have to say that my experience was that the marks were done quite well there. I don't like the way it's set out in the mark scheme, so I'm going to show you how I would set it out. Again, I just tend to write out the equation myself again, being careful to get the ratios right. Now with titrations, you really only need to write the first 2 substances, and given it's already balanced for you, you're good to go. But I do think it's worth writing the ratio of 2 to 1. You'll then fill in the data that you're given. So the volume in centimetres cubed, please write the units, because remember, if it's in decimeters cubed, you have to times by 1,000 to get centimeters cubed. Or you convert to decimeters cubed and write it in decimeters cubed there. I don't really mind, because this is in moles per decimeter cubed. Or if you prefer like that, so moles per decimeter cubed. Okay. So you're told you've got 25.00 of hydrochloric acid. You're told you've got 23.50 of the barium hydroxide solution. You're told you've got, so before you might have noticed I wrote mole per litre like that. You can write it like that or like that. Same thing. Concentration of the barium hydroxide is 0.1 mole per litre, and you can work out then N in moles by using the equation which hopefully you've learnt, which is, I'll write it down here, the number of moles is equal to the volume times the concentration. Now that's right if the volume is in decimeters cubed, but usually with titrations it's in centimeters cubed, so we tend to divide by 1,000, right, if that's in centimeters cubed. Okay, so that equation is one that you should learn, memorize before your exam, because this titration will almost certainly come up. Okay, so you do volume times concentration divided by 1000 to work out the number of moles of barium hydroxide, and that comes to 0.00235. Okay. We're trying to, by the way, we're trying to fill in this gap here. We need to use the moles to help us get there. To get there, we times by 2, because it's a 2 to 1 reacting ratio. 0.0235 times 2 is 0.00470, so we get a mark for that. And then we just have to rearrange this equation down here, so I'll just squeeze down here. So number of moles times 1000 divided by the volume is equal to the concentration. That's simply a rearrangement of that. So the 1000 has come up here. To get the concentration on its own, the volume has gone down here. That's all I've done there. So it's 0.00470 times 1000 divided by 25, and that came to 0.188, and that was done really quite well, I have to say. Right, the questions coming now are kind of tricky. So another student did the same sort of thing, chucked in some acid, some sulfuric acid this time, barium hydroxide. Now, interestingly, that gave barium sulfate. Now, you might remember that barium sulfate is insoluble, because that's the test, isn't it? For sulfate ions, you chuck in, the test for sulfate ions is you chuck in barium chloride or barium ions, and that gives you insoluble barium sulfate, which is a white solid, and that's the test for sulfate ions. But anyway, that's important in a moment. So the electrical conductivity started up here, 2.5-ish, went down to 0 once 30 centimeters cubed roughly of barium hydroxide had been added. So what's going on there? Well, over here on the left hand side of the equation, you've got lots of ions in solution. You've got hydrogen ions from the acid, you've got sulfate ions from the acid, you've got barium ions from the barium hydroxide, and you've got hydroxide ions from the barium hydroxide. Now, in this reaction, the barium ions and the sulfite ions combine to give barium sulfate, which is not in solution anymore, and the hydrogen ions and hydroxide ions combine with one another to make the water that's over here. So, no, what does it say in the last scheme? So there are no ions that are free to move. No ions free to move gets the first mark, and then you have to explain that by saying the barium ions and the sulfate ions combine to give barium sulfate, which is an insoluble solid, and the hydrogen ions and hydroxyl ions combine to give water, liquid water, which is covalent, and of course that doesn't conduct either. Many of you think the water conducts. It really doesn't conduct very well at all, because it's a simple covalent, or a molecule that doesn't conduct electricity. But if you chuck in barium hydroxide solution, again we've got barium ions in solution and hydroxide ions in solution, and they are free to move. So the barium ions and hydroxide ions are free to flow or to move, and they can carry the charge through the solution. Okay, and that's it for the first part of the paper.